Okay, so we're building up to actually classifying all the isometries. We've seen all of them now. So all isometries are either a rotation or a product of a rotation and a reflection through the x-axis. And such a product is actually just a reflection in a line which is different to the x-axis. Okay, so maybe I should write out the relations again briefly. Relations were products of rotations, seamless rotations. Here. You can move a rotation through a reflection, so to speak, at the cost of getting a minus sign, and reflection squares to the other. This is a subgroup of the group of isometries of a circle. Okay, so to check something's a subgroup, we have to check that it contains the identity. Well, n equals 0 and theta equals 0 does that. We need to check its closed under multiplication, and we need to check that it has inverses for all its elements. So it's closed under composition by what we did last time, or rather, sorry, by the exercise that I stated last time. So that's exercise L33, we should do that. So let's just do the fact that it has inverses. Okay, so that's just a calculation. So let me write down the inverse. So that's an arbitrary element of the group. So remember, these are the elements of these groups. This group is a function from S1 to S1, and the operation in the group is composition of functions. So there's a particular function from the circle to itself, and if I multiply it on the right, that is, I precompose, and multiplication in the group is precomposition by that element, which is another element in the group. I claim I'm going to get the identity at the end, and that will prove that the inverse in the group belongs. The inverse in the bigger group belongs to this subset G. Okay, so if I take this identity and I just iterate it, well, then just imagine moving the r theta through, and each time you get a multiplication by minus 1. I could just collapse all the t's, obviously, with the third identity. Prove that way too, it doesn't make any difference. Okay, so by the time you get to the end, you will have gotten n multiples of minus 1. Okay, dot, dot, dot. And whenever you see a dot, 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 you should supply a proof by induction. You know how to do proofs by induction. And once you get to a certain point, you don't have to spell them out all the time, but if you're rusty, make sure you can prove statements like that by induction. Okay, so applying that here, what does that mean? It means that I can, so just writing these all out as compositions of functions, I can move this guy through to the other side, reading that relation backwards, and I pick up a minus 1. The Tn has been moved through. Okay, so adding those two, of course, that's r psi plus or minus psi, and then I get a t squared to the n. That's r0, that's the identity to the power n. So that's just okay, so as I said, the fact that it's closed under composition was part of the exercise, so we only had to prove inverses were in there, and they are. equals that's been added to the lecture notes since the first version was put up, so if you don't see it in your version, then download it again. Okay, so what is that saying? It's saying that every isometry belongs to G. That is, every isometry is a product of rotation and a reflection. Okay, so what's the first surprising thing about that step? Well, these are linear transformations, right? R, theta, and T, they're both linear transformations. There's no obligation of a generic isometry a priori to be linear. Right? An isometry from a metric space to itself is just a function, any function, which preserves the distance. That's it. It doesn't have to be linear. Right? So I'm claiming in particular that every isometry of S1 is a linear transformation. For the duration of this proof, I'm going to write the dot product in R2 using these angle brackets, simply because otherwise I have to draw twice as many brackets, as you can see. It's tedious. So the angle brackets just mean the dot product. Okay, so what have I got to show? I've got to produce theta and n, right? So we have to show f is equal to r theta t to the n for some theta and n. Okay, but before we do that, let's prove that f is linear, right? If we could show it was of the form r theta t to the n, we would have shown in particular that it's linear. Let's do that part first. Because these transformations, I mean, to say they're linear is to say that they act by multiplication by a 2x2 matrix. Right? So first, let's show there exists a 2x2 matrix with FV equal to A times V for all V in S1. Okay, again, I notice I'm switching around with my notation. So last lecture, X and Y with no underlines indicated points in S1, just because X and Y are generic points in a metric space. Now I'm writing underlines because I'm using the fact I'm sitting inside R2. But all I'm saying is, right, so for an arbitrary point in S1, identify it as a column vector, and then this is the plane. All right, well, what does A have to be? I mean, if this worked, what does A have to be? There's only one possible candidate. Right? And I don't know that it's true, but if it was true, I can just write down what A has to be. What does the first column of A have to be? Yeah. You're jumping ahead a little because you know it looks like a rotation. That's true, right? Exactly. But I'm not claiming there's a theta around here. I've got f. If f was of the form f of v equals a times v, what does the first column of A have to be?
Wherever you just send 1, 0, 2.
Yeah, exactly. Okay, so in particular, so if this were the case, well, the first column of A would be, well, A times E1, right? But if this were true, A times E1 would have to be F of E1. And similarly, the second column of A would have to be wherever 0, 1 goes to. Well, when I'm reading it out loud, I'm saying it as a row vector. Okay, so maybe this matrix doesn't work, but there's only one possible matrix that can work, so that's what we take as our record. Okay, so we set A to be the matrix whose first column is F of E1 and whose second column is F of E2. Right? Those are points on S1. Evaluate F. I get another point on S1. Read it as a column vector stacked on together. Right, so now we just have to prove this identity is true for this particular A. Okay, so how are we going to do that? All we know is that F is an isometry, right? So we're just going to have to use that somehow. Being an isometry means it preserves angles. So let's just translate that preservation of angles into preserving the dot product. So that's what I'm saying. Okay, so what's the proof of this claim? Well, say I'm using the notation from the earlier lectures, right? So this is cosine theta, sine theta. Fv in principle is just some other point on the circle, and Fw is some other point on the circle. Okay, so let's calculate. I mean, the point is that the dot product can be derived from the angle, and the angle is preserved by F. So what's the dot product? Fv and Fw. I don't mean misled. I mean, this is just, I really mean F of Vf is a function, it's not a matrix. If I forget to write the brackets, it's just, it's a notation. So sometimes you drop the brackets when you're evaluating a function. Okay, so what is that? Well, the dot product, given that these are length 1 vectors, right? This is just the cosine of the angle between them, and I can just use the difference because it's an even function, so no matter whether it's the other way around. But that's cosine of the arc distance between Fv and Fw. Right? The arc distance was either the absolute value of this, or it was 2 pi minus the absolute value of that. But if I stick either of those numbers into cosine, I get the same thing out. Right? So this is correct. All right. But by assumption, F is an isometry. So this arc distance is just the arc distance from V to W. And by the same reasoning as in the first step, that's the cosine of theta minus theta prime, which is this. Okay, so that's just a translation of the fact it's an isometry in the language of inner products. Okay, so that's the first claim. So I'm trying to prove that F of V is equal to A times V for all V. Now let me deduce one thing, second claim from that first claim. May not seem like it did. Yeah. That's great. Claim 2. Okay, if I take 2 points on the circle and pair them, applying F to the first one or F inverse to the second one, then I still have the same number. Okay, what's the proof of that, given what's on the board? F inverse isometry. Yeah, that's true. But claim 1 applied to any isometry, that's correct. So I can deduce immediately from claim 1 that F inverse V, F inverse W, P inverse V, W. This is a little different, right? Yep, that's correct, but I want a little more than that.
The inverse is an isometry term.
F inverse is identity.
Yes. Okay. There's two statements. Together that gets it. Right. So let me rewrite W as f of f inverse. Now, that's definitely true. But now I can use claim 1, right? So that's it. I believe claim 2. Okay, so now we're ready to prove this idea. So take any vector in S1, right? Well, then we can write it as, say, lambda E1 plus mu2, of course, so lambda squared plus mu squared is 1. And let W be arbitrary. Okay, so V and W are both arbitrary, but I'm using lambda and mu to give the coordinates. So let me compute f of V comma W. Let me just explain how to do it. That's V comma f inverse W. Okay, but now the dot product is linear in both variables, right? If you put a linear combination of vectors in the first position of the dot product, what you get out is a linear combination of their dot products, right? So using this expression for V, I can write this as lambda E1, comma, f inverse W, plus mu E1, f inverse W. But now E1 and W are again just arbitrary, well, they're not arbitrary, obviously. They're points on S1, so I can use claim 2. That's lambda f of E1 W plus mu f of E2 W. So the point of that little dance backwards and forwards is that I don't know that f is linear, but it behaves like something linear within the dot product. That's what I'm just observing. Okay, but what's f of E1? F of E1 by definition is A of E1, right? The matrix A was set up so that A times E1 was F of E1. So that is A of E1. W. Same for E2. And now I really need matrix multiplication. Okay, so this was linearity of the dot product. And using that again, I can take the linear combination matrix. Lambda E1 plus mu E2. But matrix multiplication is linear, so that's A times lambda E1. So that's just okay. So where did the fact that f is an isometry enter? It entered in claim 2, which was used twice. Right? That relied on claim 1, which relied on f being an isometry. Okay, so what have I shown? I've shown that f, v, and av, they're two vectors. When I pair them with anything, I get the same number. So I claim FV therefore equals AV. Why is that? Why is the consequence of that identity of the two vectors FV and AV must be the same? So So this identity holds, so fix V, it holds for all W, at least all W in S1. Right, and that's enough. Well, we can just take W to be E1. Right, read this identity for E1. What happens when you take the dot product with E1? You read off the first coefficient of the vector. Right? So FV and AV, there's some vectors. You pair them with E1, you read off the first coefficient, and they have the first coefficient by this equality. And doing the same with E2 will show you that the second coefficients are the same. So they're the same vector. Okay, so what I've done is I've proven that, we're not done yet, but I've proven that F is linear. It's given by multiplication by F. So that wasn't a priori. So now I can prove that, so we started with an isometry, and now I've proved it's linear. I now need to prove that not only is it linear, but it has this special form. Okay, any questions about this approach? Okay, so line 3. Claim either A is already a rotation matrix, or T times A is a rotation matrix. T is this matrix. Prove. Well, prove that one of two things is true. Suppose one of them isn't true and then prove the other. Okay, so suppose A is not a rotation matrix. But we know it preserves the inner product, multiplication by A, right? Because that's claim 1, now that I know that FV is A times B. So exactly what was in the exercise. So the point of the exercise was to get you to prove this. I know we've done the exercise yet, but if something preserves the inner product, read the inner product as a multiplication of the transpose of the matrix, and then think about V and W ranging over all vectors, and you'll deduce. So I'll put up solutions to that exercise at some point, so there's no gap in the lecture material. So from the fact that it preserves the inner product, we can read off that the transpose of A times A is the identity. Well, therefore, the determinant of A squared is 1. Take the determinant of both sides. Okay, so either the determinant is 1, in which case, by the exercise that I'm referring to at the end of lecture, I think it's lecture 2, if the determinant is 1 and it preserves the inner product, then it must be a rotation matrix. That's just a calculation. So assume the determinant is 1, that gives you some polynomial equation on the entries of A. Take these polynomial equations in the entries of A. You'll see something like A squared plus B squared equals 1. That means A and B must be of the form cosine theta sine theta from some angle. Just play with the algebra. You'll see that you must get this. Okay, so A must be, if the determinant was 1, then A must be a rotation matrix, in which case we're done, right? We've proven that A, and therefore F, is of the form R theta. If the determinant of A is negative 1, then the determinant of T times A is negative 1. Because the determinant of T is negative 1 and the determinant is multiplicative. And TA preserves the inner product. So then we can apply the same argument to TA. So TA must be of the form r theta, and therefore multiplying both sides by t, A must be of the form t theta, well, that is. Okay. So either way around, we find that A belongs to the subgroup G, and therefore F is in G. So that's all the isometries. There's an exercise at the end of the lecture which explains how a product of the reflection and the rotation is again just a reflection within the line.
Is the determinant of TA 1?
Yeah, that's right. So the determinant of TA will be the determinant of T times the determinant of A. If the determinant of A is -1, the determinant of T is 1, I mean -1. So then it'll be
Because you want to be very careful.
that was the question, yeah. I agreed and then wrote the other thing next.